Thank you very much, Cora, and thank you very much, organizer, for having this amazing workshop. I'm learning a lot, and I'm Ken Osato from Chiba University in Japan, and I also talk about the field level inference, but using the different type of the for the modeling, so GridSPT. So this is collaboration with my former collaborators, from Takahiro, also in this room, and Chitaria from the Kyo team, and also US team, and also Oliver and Thomas and Florian Jens also in this room, so from BN team. Okay, so let me first give you some introductions. Probably you already seen this many times. Probably I just go through very quickly. Actually, so we want to extract information from the observed distribution of the galaxies. So that is now called the galaxy clustering. So that is the main theme of this workshop. So what we observe is over the galaxies and the matter. The matter is a direct consequence of the gravitational evolutions. So we want to extract some information from these galaxies, but this is actually biased traces. Then we actually rely on some techniques to relate between the observed galaxy to the matter. So that is of course matter connection. So that is. So and observe this 3D distribution of the galaxies. Of course, we have to rely on some technique on the. So in this case, in our case, actually, it's field inference, or more conventional actually, we have so far we have used the statistics. Both 2-point statistics has been very powerful to constrain the cosmological models. So that is just one key example from the observed by STSS. So we can measure the power spectrum from the 3D distribution of the galaxies. So so we can of course the matter distributions, also the energy fluctuation at the early universe, and also can constrain the dark matter models from the in particular for the small scale measurement. That is I'm showing here one of the key example from the SDSS. But now we are expecting more data come from the stage 4 survey, like DAISY has already published data, and Euclid now taking data as well, and also PF. For me, actually, I'm deeply involved with the SWAR PFS, which also the spectroscopic surveys read by in particular by the German Institute, also including some partners from the US and Europe as well, and we will observe the additional galaxy clustering at high density. Okay, so that is basically the probably already we have with. But I also want to get back to the power spectrum analysis. As you know, actually this is the most fundamental. Actually, this is just statistical level expression. So power spectrum. So that is most fundamental statistics in galaxy clustering analysis. Of course, that is has the complete information if the field is Gaussian field. So probably. So as you see that, so for demonstrating that, so I just pick up from the nonlinear density field, matter density field from the anybody simulations, and also just a random Gaussian random field. Probably by eye it looks completely different. However, so if you measure the power spectrum, it's completely identical. Because the trick is that I just measure the power spectrum from this nonlinear density field and just rotate the space, and then we generate this type of this. Even by eye, we can distinguish between these two. So of course, and naturally, so we can expect some more information beyond power spectrum or beyond the Gaussian random. Natural expectations about this. Why we are now interested in the field level inference. So probably we already have heard about the field level inference several times. So this is a kind of the definition or the setting the field level inference in this case. So field level inference, as you see that we see that so instead of relying the summary statistics like 2-point statistics or bispectrum or power spectrum, the posterior actually I'm here defining in the here it's a log posterior is just given the observed number density field, for example, given observe the 3D distribution of the galaxies, and then we want to constrain the basically we want to constrain the cosmological parameter like omega matter or sigma 8, and also we also want to constrain the initial density field, so they're not by this field S. And we just take the difference. In this case, I'm just showing the Fourier space likelihood. So previous work done by the Fabian's group, and also we have also got interested work by Kazu as well. And also, yeah, here I'm just taking the just most simplest form of the Fourier space likelihood, just taking the difference between observed field and so theoretically a predicted for the model number field. So that is also one of the main topics. So just taking, yeah, this is also quite, say, under debate, but maybe this is the main topic of this, yeah, discussion session. Anyway, so just choice of the likelihood is, yeah, quite technical. But anyway, so in this case, I just take this Gaussian likelihood to define the possibility. So yeah, and another very important component in the field level inference. So as we see, so that is of course the field level. So forward modeling. So yeah, given the cosmological parameters and the initial density field, we want to evolve the density field to the nonlinear density field or nonlinear galaxy density field to make the direct comparison between the predicted one and observed one. So yeah, in the last two talks, actually Thomas and Florian just introduced the disco DJ. It's very efficient and very accurate for the modern technique. But so far we have been using the LPT and particle mesh. That is also quite useful to serve as the for the modeling in the field level. That is the setup. So yeah, and I want to introduce another type of the forward modeling, which we call the GridSPT forward modeling. So yeah, I'll just list some challenges and bottlenecks of the forward modeling. Of course, forward modeling is not so cheap actually because compared with calculating the power spectrum by spectrum, it is computational cost is relatively high. So that is one of the challenge. So another challenge in the statistical analysis because we are now working on the high dimensional parameter inference. So yeah, because we have a very high dimensional initial density field, it's typically 10 to 4 or 10 to 6 the degree of freedom. So that is we want to solve in this. In this work, we have developed the Eulerian based GridSPT algorithm, so which also adds some modifications by utilizing the other GPUs and also the automatic differentiation, which is also essential to conduct the high dimensional parameter estimation. Okay, so let me give you some quick background and introductions about the GridSPT for the modeling. So at this point, actually, we don't have any functionality about the GPUs and anyway. So yeah, this is original work by Atsushi and Takahiro and Donhi. So yeah, GridSPT is basically complementary to the LPT or Lagrangian-based technique. So we solve the SPT standard perturbation theory, so Eulerian evolutions at the grid level. So yeah, because we are starting from the fluid equations with rotationality and a single stream approximation. So the differential equation what we want to solve is summarized here. So this is the time evolution of the density field and the velocity divergence field and some mixing matrix. So in this ancient digital cases, it's just constant matrix. And also, that is the source term, differential operator with the density and the velocities and velocity divergence and velocity reduced velocity. So starting from this master equation, so we actually expand this differential equation with the perturbative approach. So the delta and theta and velocity as well. So this is also expanded in a perturbative manner. So then we can finally have a recursion relation like this. So this is the delta n is the order of the perturbative expansion. So starting from the n equal 1 is linear. So then we can just using this recursion relation to get the nonlinear evolutions. So based on the SPT framework. So of course this is infinite series. So we have to truncate at some point. So that ensures that the computation can be done within the real. But anyway, so in practice we actually truncate n equal 5, which gives you the reliably give you the good match with n-body nonlinear density field. So that is the result actually. So this is the density field for just slice of the n-body to compare with the n-body nonlinear density field. So the left one is the GridSPT and the right one is the n-body density field. And and the by eye it looks fine, but also the also the 1D. So for example, this high density peak. So you can just look at just 1D density fields, then actually this is the GridSPT result. So if you add more nonlinear contribution, n equal 1 to 5, that is gives you a better match with the n-body simulation result. So and also gives better match compared with the 2FPT. So that is how the GridSPT works as for the modeling. And for the statistical level, so we have already, they have already checked the power spectrum level, and also, so here I'm showing the power spectrum compared with the n-body and just a SPT2 loop as well. So of course, because this GridSPT, of course, it's also based on the SPT framework. So that gives you the quite consistent results with the SPT. So this is solid line is just SPT2 loop results. So analytical results compared with the blue one is come from the GridSPT2 loop for a given realization of the to be consistent. This is just up to 2 loop orders. And our colleague Chen Yang just read the paper to describe the so-called NEPT, nth order Eulerian perturbation theory approach. So that's in that case, we add order, we add contribution from the up to 5th order everything. Actually, that is in a sense actually it's a heterogeneous contribution. Actually, that is not ordered by the linear density order, but we found that that gives you a better match n-body power spectrum. Also, we have to include some counterterms anyway, but we get quite a nice agreement with them. The cyan line corresponds to this. If you include the density contribution up to 5th order. Okay, so let me talk about the challenges and the bottlenecks to how we can solve that bottlenecks using that. So the main bottleneck, computational bottleneck in GridSPT, because we many have many 3-dimensional FFT in this recursion relations. So each differential operator involves a 3D FFT. So we want to speed up by some ways. So that's why we have used this accelerator. Probably you already know that. So GPU are now very powerful at solving such a highly parallel problem. So then we have implemented the GPU-based GridSPT for the modeling. Then finally we get, this is not so fair comparison, but anyway, so we can get a very high speed using the just one NVIDIA 800 GPUs around this supercomputer. Okay, so the next topic is about high-low number density field. So halo part is basically simple. Actually, just applying the bias expansions up to just quadratic order. So this is the halo number density field. So from the GridSPT ones, that's the density, the linear density field, and also a square, the k square. So this also can be computed using the nonlinear density field up to 5th order, and also adding the higher derivative bias as well. So to model the halo number density field. Okay, so the next one, so probably I can just skip this one anyway. Just go quickly. So of course, we have high dimensional parameter space. So of course, Hamiltonian Monte Carlo sampling is super powerful for solving such exploring the high dimensional parameter space. So that is approach here. And of course, if you want to make use of the Hamiltonian Monte Carlo, you also need gradient information with respect to each parameters. So that's why we have also used the JAX library, which gives you the very efficient, also provides you with the auto differentiation functionality. That's already discussed by many people, including Thomas as well. Okay, so and the differential GridSPT we have we have just named as this code as a differentiable GridSPT. So the solving the GridSPT equations can be fully treated by the JAX library and making use of the GPU acceleration, the 3D FFT part. And for posterior sampling, so HMC no U-turn sampler, so that is also made by powered by this NumPy library, which also makes of the GPU acceleration. Okay, so in the next few minutes, I'd like to give you some preliminary results of the field level inference part. Just to test our approach. So using the n-body simulations. So this is the basic setup. So cosmological parameters are basically only 2. So matter density field, the omega matter, and the scale sigmoid, just sigmoid divided by the total values. And the shear density field defined in the regular grid as a 256 cubic grids. And also target field is the halo number density field taken from the just a standard n-body simulations. Yeah, this mass range and the number density is around 2 times 10 to minus 4 inverse of the unit. Yeah, this again from the Fourier space likelihood is rather simplified. And yeah, also in addition to the cosmological parameters and shear density grids, we also sample with the sigma epsilon 0 and sigma epsilon 2. So this is the running variance of the GS likelihood term. And also, yeah, of course, I didn't show that, but of course, we want to also sample the bias parameters as well. And actually, so we found that actually this is quite hard to sample without any prior information on the bias parameters and also the cosmological parameters. So yeah, in order to get a reliable, reasonable result, we had to impose a prior on the linear bias because there are a lot of the parameters which regulate the amplitude of the initial density field. Initial density field, also alpha, and also B1. So they are all changes amplitude. So that's why we just stick to this Gaussian prior on the linear bias. But this is expected from Tinker formula and also virtual measurement of the bias spectrum. Yeah, this is quite tight, almost fixing the linear bias parameter. However, but we don't have to include any priors on the other bias parameters and other sigma epsilon 0 and sigma epsilon 2 and also cosmological parameters. Okay, just give you very briefly what the current status of the field level inference. So this is our intercept parameter, omega matter, and alpha. This is 1D marginalized posterior. So this blue one is of course the marginal posterior with the Kmax 0.08. Okay. And yeah, it's somewhat biased actually because of the due to finite volume effect anyway, but still within the 2 sigma ranges. So this orange bar corresponds to ground truth, so roughly 10% or p-value 10%. So for other parameters, so the B1 and other bias parameters are very constrained. However, so sigma epsilon 0, sigma epsilon 2, so it's fairly far from the convergence actually at this point. So yeah, this is has a very notoriously long correlation time. So anyway, we can just run more samples to get better convergence. Okay, and the last one is quite preliminary, also the preliminary result, and we are now still working on the hard on the how to figure out. So this is a constraint. This is a black constraint on the omega matter and alpha, and with a different Kmax, okay, 0.06 or 0.12. And this black dashed line is the ground truth value, which I showed in the previous slide. And this is a constraint. Yeah, constraint shrinks, but somewhat biased, even for the Kmax 0.06. The right one is the power spectrum reconstructed initial density field. This is actually map the maximum a posteriori initial density field. So this blue dashed lines the ground truth actually input initial condition power spectrum. So if you choose the 0.06 relatively limit only up to the large scale, that can actually bias ones also get we get that one. And 0.12 that is maybe too small scale. Then we can also get some. 0.08 to 0.10, maybe, this is maybe sweet spot, so we can correctly reproduce incident. But anyway, there's a caution about that. We have introduced some informative prior on the linear bias, so that may, quite problematic in the real data analysis. Okay, this is kind of a summary and the prospects and the what we get in the next. Of course, we need to compare with the P plus B analysis. So that is the main topic of this workshop. So we actually the building blocks are already ready. The estimator utilizing the JAX. So this is already written by Thomas already. And the covariance also can be measured with the GridSPT framework. Also, number of degrees is a bit also problematic in the Eulerian perturbation theory because we also need a high resolution to get a convergent result. So maybe, just currently using just single GPU, but we can make use of the JAX comp or the sophisticated library to get distributed memory, efficient merge GPU effectiveness. So that is also one of the prospects in this. And we also have, maybe 8 GB is not so enough. Maybe we will have more realization of the n-body estimation. Better discussions of the convergence of the. Okay, so this is the last slide. Probably I'm just running out of time. I'll let just here, and I'm happy to take your questions. Thank you very much.